Okay, can you guys hear me? Yeah, good. Right, my name is Robert Smallshire. I work for and part own a small consultancy based here in Oslo and in Stavanger. I'm part owner of 60 North, and we do work around the world in a variety of technologies. Currently we're doing work in Puerto Rico, we do a lot of work in Oslo, also work in London. So we get around quite a bit. And although we're not technology specific, Python is a tool that we come back to again and again. And I'm not sure how many of you here are familiar with the details of Python. A lot of this talk is very accessible. Python code is very readable. So even if you're not familiar with the details of Python, hopefully you can get a good understanding from this talk of what coroutines are and how they work and how they facilitate concurrency, not just in Python 3, but in any language which supports some more basic primitives. So although all the examples I'm going to show you today are toy examples for the purposes of illustrating what coroutines are all about and how concurrency works in Python 3, I think it's important to point out that a lot of what I've learned and my exposure to coroutines and asynchronous I/O in Python is based on industrial practice. So I last year worked on a system for a company in London which does what's called demand response management for the power grid, and where I was writing actually embedded Python programs that run on small Odroid single board computers distributed on industrial sites to control power flow to and from those industrial sites based upon real-time electricity pricing in the UK. More recently, I'm involved in a nascent startup here in Oslo. It's so new that it doesn't even have a name yet, where we're involved in solar power prediction and monitoring, also using async I/O as one of the technologies we use to build our services. I'm also a maintainer of a thing called PySerial async I/O. You might think of serial ports as being those old kind of 9-pin D connectors on the back of your old computer going way back, or even further back, the 25-pin D connectors, and you probably think that serial ports are rarely used these days. That's not the case at all. Almost every device which has sensors in it is going to have serial ports on board. So serial ports are a hugely important thing, and we're beginning to see use of async I/O in Python to deal with serial input and output. If anyone wants to help me make this work on Windows and understands Windows I/O completion ports, please get in touch. I'm also the author, or co-author, I should say, of 3 books. So for those of you who are maybe not familiar at all or very familiar with Python, then please look into our books, and if you want a free copy of these, come and see me afterwards and I'll see what I can do. So, onto the structure of the talk. I'm going to talk about why we care about asynchronous I/O. Why is this something that's important to us? Why do we need to solve this problem? Then I'm going to move on to explaining what coroutines are, and we'll do that independently of looking at input-output. We'll just try to explain coroutines, and in fact we're going to build something in Python that is equivalent to what the modern Python language gives us, but we're going to build it from the ground up, from first principles, without using async I/O. We're just going to do it from scratch as a learning exercise. Then we'll move on and look at what the language and library gives us in Python, and then only at the very end am I going to get onto the actual I/O aspect, and we'll plug all this together. And if we have time at the end, I'll finish with a quick demo. So, what is asynchronous I/O about anyway? Well, input-output is high latency certainly compared to the speed of our CPUs these days, and as such, sequential programs spend a lot of time waiting on I/O. So you want to perform some I/O with an external device, a disk or a serial port. You spend a lot of time waiting for the data to come back to you after you've requested it. So hitherto, the traditional response to this has been to have multiple threads or multiple processes. More recently, we've seen things in Node.js which use a similar approach to what I'm going to talk about today. The problem with the threading and multiprocessing approaches is there are large resource overheads. On Linux, every thread is going to carry with it at least 8 megabytes of stack space, even if you don't use that. And there's a large cognitive overhead to using these. Reasoning about shared mutable state, communicating between threads is obviously where a lot of the complexity comes into working with these kind of systems. And in Python in particular, we have to remember that the entire Python interpreter is a big pile of shared mutable state. That's what it is. And that shared mutable state in Python is protected by the now infamous GIL, or Global Interpreter Lock, which really prevents Python making use of additional compute resources that we give it. Okay? But it turns out that because programs spend most of their time hanging around waiting for I/O, taking advantage of additional compute resources isn't actually so important for many applications. What we want is for the I/O to go quicker. So I want to establish a few definitions. For many of you, this should be, it's probably stuff you know already, but I just want to make sure that the terminology I'm using I use during this talk is something we can agree on. So concurrency versus parallelism. Concurrency is about dealing with multiple things at once without necessarily doing multiple things at once. So tasks which overlap in time, their start and end times overlap, although we're only progressing one of those tasks at any given instant. And so coroutines, which I'm going to show today, are very much about concurrency. On the other hand, we have parallelism, where tasks are actually running simultaneously. And of course, to do this, we need more than one computer or more than one core with multiple threads. So I'm very much going to be talking about concurrency today. Another word that's going to come up is asynchronous. So essentially, there's no need to wait for a result before proceeding with other work. And of course, when we can do this, the overall duration becomes shorter, which is a good thing. We're less waiting on the latency of the I/O. Versus sequential or synchronous. It's interesting that the word synchronous, which is obviously the opposite of asynchronous, in common day usage, synchronous means doing multiple things at the same time. But us computer people have inverted that meaning to mean doing exactly one thing at the same time. So we've kind of screwed up our linguistics a bit here. But it essentially means we must complete something before proceeding. And of course, then the overall duration is longer. Another way of thinking about asynchronous and its opposites is asynchronous versus non-blocking. So the way we use it in what I'm going to show today, asynchronous code returns immediately, essentially with the promise of some future and complete result. Versus non-blocking, which also returns immediately, but it may return immediately with no result, a partial result, or a complete result. And essentially we need to poll something in order to figure out when the complete result is finally available. And then we can think about preemptive multitasking versus cooperative multitasking. So preemptive multitasking is where the scheduler interrupts the tasks that we're running concurrently, and the tasks have no say in when they are interrupted, which of course means your tasks are interrupted at the most inconvenient moment, which means that we have to protect any shared mutable state with locks, so inconvenient context switches. And of course, preemptive multitasking requires some parallelism. So even if you have one core in your computer, there is hardware-level parallelism going on. There are CPU counters, hardware counters, which are counting down, ready to generate an interrupt to force a context switch. Versus cooperative multitasking, where tasks have to deliberately yield control back to the scheduler. So this is nice in many ways as a programmer, because then we get to choose when we're interrupted. Okay, so that can obviate the need for locking. On the other hand, if we forget to yield control to the scheduler, we can essentially hang the whole system. We can cause things to grind to a halt because the scheduler has no means of interrupting, of preempting our task. So with async I/O and coroutines, we're very much on the cooperative multitasking side of the equation here. So the promise of async I/O and coroutines in Python is that they allow us to write asynchronous, concurrent, cooperative tasks in a sequential style, which is great because it means the reasoning about how these things are working becomes much more straightforward because we're essentially thinking about synchronous programs again, which is what we've been doing for years. But at the same time, we get some of the performance advantages of not having to wait on high latency input-output. So that's set the scene, if you like. Let's move on to actually looking at how coroutines facilitate concurrency, and in fact, just what is a coroutine? Let's try to answer that question as well. And in this part of the talk, I'm going to build something that is functionally equivalent to a very important part of Python's async I/O, but we're going to do it from first principles, from the ground up, without using async I/O at all. And essentially, what I'm doing here is I'm recapitulating the journey I went on when I was first exposed to this stuff. I find it's very useful when I'm trying to understand something to try and build something simpler, but which essentially does the same thing. And then by the time I've solved that problem, then I have a really good understanding of what's going on. I think it's very important when you're using a technology to be able to have some appreciation of what's going on one level of abstraction down from the level at which you're writing your program, your application code. Because when things stop working or behave in odd ways, you have some insight into what's actually going on. And I find that actually building simple versions of things I want to use from scratch is a very good way to do that. So that's exactly what I'm going to go through now. Before we get to that, though, we need some code to actually do some work. We have a pact in our company that we are not allowed to use the F word, where F is Fibonacci. And so in this example, I'm going to use a thing called the Lucas sequence, which is closely related to the Fibonacci sequence, but just has a different initial starting condition. And so what you're seeing on the screen here, on the left, is a Python generator function. And we know it's a generator function because it has at least one occurrence of the yield keyword within it, which you can see on the penultimate line there. In fact, we have two occurrences in this. And the Lucas function just generates an infinite sequence of numbers. On the right here, I'm importing that function. I'm also importing a thing called islice, which is like take. It just takes a certain number of items from a sequence and and converting those into a list. So I'm taking the first 10 Lucas numbers. There we are. Okay. Now, there's no concurrency or anything going on here. I just need some code that's going to do some work. That's the only reason we have this here today. The next function I'm going to introduce is search. And search is also a very simple Python function. Even if you don't know Python, I hope you can read this. So search accepts some iterable series of data and another function, a predicate function, and we test that predicate against each item in the series. And if the predicate returns true, we return the matching item. If we get to the end of the for loop without having found a matching item, we raise an exception called value error. Right? This is a very, very straightforward Python function. Again, no concurrency here yet. So search is just a regular function, and here you can see on the right, I'm asking for the first Lucas number that has at least 6 digits. Yeah, I'm just converting the Lucas number to a string, checking how long the string is, and we can see that the first Lucas number with at least 6 digits is 103682. Very, very simple Python code. I hope you can all understand this. What we'd like to do is turn our search function, which is completely non-cooperative, into a cooperative search so that it can yield control to some other piece of the program. And all we need to do to make that cooperative is to insert a yield keyword. So we're just going to stick yield here inside the loop so that we yield once through the loop. And notice that we're not yielding anything. This is a shorthand in Python for yield none. So none is like a null or nil object. So we're not yielding anything, we're just yielding, which will interrupt the flow of this loop. And to remind us that this is now a generator function and not a regular function, I'm going to rename it to async search. So let's see how to use async search. I'm going to import it and the Lucas generator. And I'm going to search again for the first Lucas number. And this time we're going to search for the first one that is greater than 10. Okay, so not with 10 digits, but actually just greater than 10. So what is G? Well, when we call G, we get not the result, we get a thing called a generator object. Okay, so the generator object encapsulates the running state of this function. Okay, and the generators in Python are also iterators, and so to advance an iterator in Python, we pass the iterator to the next function. So we do next G. And every time we call next G, we're running one more iteration of that loop until we get to the yield again, and we stop, we pause, we suspend execution of the function. Okay, so we've run one iteration now, and we can run another iteration. And you'll see that next isn't returning anything. Well, that's because yield isn't yielding anything, right? So let's do another one. And so we can advance this search one iteration at a time. Now, it's not immediately obvious when I'm doing this, but I can actually do more than one thing concurrently here. While our search function is running, I can start doing other stuff, right? I can print hello world. So now we have concurrency, right? Using nothing more than iterators, okay? Now I'm printing hello world and running a search. And we can keep advancing the search with more calls to next. And then eventually, next will raise a stop iteration exception. And stop iteration is how Python programs signal that an iterator has reached the end of the data. It raises an exception called stop iteration. What's interesting about Python is that that exception carries a payload, and here the payload is the item that we found. So that return statement in async search actually causes an exception to be raised by the generator machinery in Python, and the result gets wrapped up in the stop iteration exception. And you see at the bottom there on the right, stop iteration 11, that's the result. Okay, so we can use generator functions in Python to support concurrency. And all a coroutine is, essentially, is an interruptible function like this. It's a function where we can pause execution and then resume execution at the point we left off at some later time. And of course, that's exactly what we're doing here when we call next. Yeah, so I think that just says what I've just said to you. So let's make this a little bit more sophisticated and a bit nicer to use. It's not very nice having to call next and have this thing look like an iterator. We'd like it to look a bit more like a task, because conceptually that's what we're building. And thinking in terms of iterators when conceptually we're building tasks, there's a bit of a mental mismatch there. So let's make a task. All a task is a generator function called routine here, and an integer ID to identify that routine. So those of you who don't know Python, dunder init, you can think of it as a constructor. The constructor accepts routine, and within the constructor, I just take the next ID. So next ID here is essentially a static class attribute here. So the task is a very simple thing. It's an integer and a routine, a coroutine. So given task, which is a very straightforward thing, we can now build a scheduler for running tasks, right? And I'm going to show you the entire code for the scheduler. It can be a very, very straightforward, simple thing. So you see the constructor, dunder init there, for the scheduler has a deck of double-ended queue of runnable tasks. And we have two dictionaries, the things with the curly braces, which contain any completed results from completed tasks or any errors from tasks which have failed while they're executing. The next method there, add, allows us to add or schedule a routine to be run by the scheduler. And you can see it, we just give it a routine, it wraps it in a task, and it appends it to the queue. And then returns the task ID for the new task. So that's just going to return an integer. And then we have this run to completion, if I can get down to that. So this function is the entirety of the coroutine scheduling program. So you can see it's essentially a while loop, and it says, while we have some runnable tasks, pop the next runnable task off the queue, call it task, print a friendly message, and then try to pass the task routine to next, okay? And capture whatever result comes out of that into yielded. Now, when we call next, several things can happen. First thing that can happen is it can raise stop iteration, which means the task has completed. So if it raises stop iteration, you can see that we extract the result of that task from stopped value and put it into the completed task results dictionary against that task's ID. Okay? The other thing that can happen is it can raise some other exception. I mean, obviously it's a task, it could be doing anything could go wrong. If it's some other exception other than stop iteration, we capture that as E here and put that into the dictionary of failed task errors. The else block here, that's a kind of strange Python feature. Try else blocks are executed if there is no exception. So basically this says yes, next, advanced without any exception being raised. We check that we get nothing back with the assert statement there, and we take the task that we've just popped off the queue and executed and pop it back onto the other end of the queue so it can go around again. Okay, so we're just taking tasks off one end of the queue, giving them one chance to run, and putting them back on the other end of the queue. It's an extremely simple thing, as you can see. It's just a while loop. And this will keep running while there are tasks in the queue. So let's see what this looks like when we execute it. We import the scheduler, I instantiate the scheduler, and then I'm going to add my async search task to the scheduler. You can see there we're looking for the first Lucas number with more than 6 digits, and then I can run to completion. And you can see, because my queue only has one task in it, it's just getting popped and pushed repeatedly as we go around. You can see it's yielding every time. Eventually that task will complete, and there are no more tasks left. And we can pop the result out of the results dictionary there and get the answer. Great. We've basically written a while loop that calls next repeatedly and for as long as it can. And it's not very exciting with one task, but this is completely sufficient for running as many tasks as you like. So let's add 2 tasks here. So here's find the first Lucas number with at least 7 digits and the first Lucas number with at least 9 digits. Both of those tasks are added. We now run to completion, and you can see it's alternately running task 1, task 2, task 1, task 2. One of those will complete earlier because it's a shorter problem to solve. Then task 2 will continue running until we get to the completed result. All right, so very, very simple, straightforward thing. And we have concurrency, right? There's no parallelism here, but there's most definitely concurrency happening. We are dealing with more than one thing at the same time. Yeah, and of course we can get the results out. Okay. So searching for Lucas numbers is all well and good, but for the next part of the demonstration, we need to do a little more computational work, something that will take a bit more time. So we're going to search for prime numbers. So here's my primality testing function, isPrime. It's extremely naive. I wouldn't use this in production for finding prime numbers. It suits my purposes very well today. It's very inefficient, and so it takes a long time, and that's exactly what I want for the demonstration. So, determining whether 12 or 13 is prime is obviously very quick, but if some of those other calls there, like 2 to the 61 minus 1, that takes half an hour to figure out whether that is prime, because Python, for all its wondrousness, is not a very fast language. I'm also going to introduce another function now, very similar to the search function, but rather than it, another coroutine in fact, rather than it returning the first match in a sequence, it's going to print every match. It's just going to keep iterating through the iterable, and every item that matches, we're just going to print it out. Okay? And we can see it's a coroutine because we have that yield in there. So let's use our scheduler and add the async print matches on the Lucas numbers, which are prime. Okay? So you can see now that we're running, and now and again, the task will print out a message, which gets interleaved with the kind of logging messages which are coming out of the scheduler itself. Okay? So nothing too unexpected there. But you can see the gaps between the prime Lucas numbers are increasing, which is a useful property for the demo. Now, alongside us finding the prime Lucas numbers, I would like to do something else, completely unrelated. I would just like to print a message at fixed time intervals. Okay, so I have this other coroutine here, repetitive message. I can give it a message string and an interval in seconds, and every 2 seconds, say, it's just going to print that message. So you can see we have a couple of loops here. We have the infinite while loop, which just runs forever, and the inner while loop, which is essentially a sleep routine in there. Very simple function. We need to make this into a coroutine so we can run it in our scheduler. So we insert the yield at the bottom there. And as I've done with my other functions, we rename it to async repetitive message, just to remind us that this is a coroutine rather than just a regular Python function. There's a subtle bug here, and these things are subtle enough that they're quite easy to miss, and you do need to sit down and think about your code quite carefully. And the bug is that if interval seconds is really short, the coroutine will never yield. Right? So you need to be very careful about where you put the yield statements in your code. It's very easy to fix. We just need to change the ordering of things. It doesn't really matter when we yield in this routine in terms of how it behaves, other than the fact that with small numbers it might never be interruptible, or will never yield control back to the scheduler. So it's important to make sure that your coroutines either complete essentially instantaneously, they can just return a result right now, or they yield at least once. Okay? Very important property of these things. Otherwise, you've built something that can stall your whole system. So let's plug these things into our little scheduler here. So I'm going to import my repetitive message coroutine, my print matches coroutine, my Lucas numbers generator, and my primality tester. Instantiate the scheduler. We'll schedule the repetitive message. I spend far too long in airports, so this is kind of imprinted in my mind. And we'll do the Lucas numbers search. And then we'll run to completion. If my clicker works. Okay. So off it's running. It's printed the message, unattended baggage. It's going off. You can see it's running task 0 and task 1 alternately. But it seems to have stalled, right? In spite of the fact that these were coroutines, something has stalled here. And the problem is that even though async print matches is non-blocking, and we've designed it that way, our isPrime function, for small prime numbers, it returns the result effectively instantaneously. But for large prime numbers, it takes a long time to determine whether that number is prime in our horribly inefficient Python code. So the isPrime function is now essentially blocking progress of the system. And you can see it's getting hung up on task 0. And because it's getting hung up on task 0, task 1, which is supposed to be printing a message every couple of seconds, is not getting an opportunity to run. So there's a guideline here, which is that essentially everything you call transitively from a coroutine needs to be non-blocking. That doesn't necessarily mean it needs to be another coroutine. It could be non-blocking in other ways, by using threading, for example, but it mustn't block. Okay? So essentially, coroutines in these kind of programs are contagious to callees. If you are a coroutine, the things you call should probably also be coroutines, or at least non-blocking. So we have our print matches function, print matches coroutine, calling a regular function. We need to make that regular function itself into a coroutine. So we take our isPrime function, and we know how to make these into coroutines now. We just stick a yield in there. So we put a yield in the loop there. Now async isPrime is a generator. It will return a generator object when we call it. And because it returns a generator object, we need to call it differently. And the way in Python 3 we yield from kind of nested inner generators is by using yield from. This saves us having to write another for loop in the calling function to iterate the callee generator. When we do this, it turns out that this bare yield, which is a kind of term I've invented here, is no longer needed. It's no longer needed because the function we're calling on the right has the bare yield in it as well. And that seems kind of irrelevant at this point. If we left it in there, async print matches would yield to the scheduler twice per iteration rather than once. That may or may not be a problem depending on what you're doing. But the point is, it's unnecessary. And in fact, eliminating that bare yield there is an important part of a refactoring that's coming up quite soon. In fact, it's part of a refactoring that's already started, you just haven't realized yet. So the second rule is that everything that calls transitively to a coroutine must iterate the generator, because the coroutines are packaged as generator objects. So coroutines are also contagious to callers, not just callees. So you can quickly see how these two rules taken together cause your whole program to need to be written in a particular style. Right? So if you start out with a sequential synchronous program, converting it to this kind of programming style is not necessarily straightforward because of this property that it's contagious down the call stack and contagious up the call stack. So this is one of the, I would say this is an architecturally significant decision because changing your mind about how you structure your program is going to be quite costly later on. So it's one of the things you want to make your mind up about earlier on in software development rather than later. Right, so we're going to do a little refactoring now. So going back to our async repetitive message, we have the two loops here. And if you think about it, the inner loop here, with the prelude to it, is really a sleep function. It's really doing sleep. So we're going to do an extract coroutine refactoring, and we're going to pull out a separate sleep coroutine here. Okay, so now repetitive message, now all it does is print the message, yield from the sleep coroutine, and the inner loop is now moved out into that other coroutine. So this is also a very significant refactoring, as you'll see shortly. Async sleep has some interesting properties. It always yields at least once. Async sleep 0 yields exactly once. And because async sleep 0 yields exactly once, any occurrence of the bare yield anywhere else in our program can be replaced by yield from async sleep 0. Now, that might not seem like any kind of win at all, because we've replaced one word with 3 and a method call, but it is an important refactoring. And it's one of those interesting cases where on the way to simplifying code, you have to write more code, and the code kind of balloons up before kind of magically shrinking down as all these things cancel out. So that's an important step there. So then we can take all of our other bare yields and replace them with yield from async sleep 0. And when we do that, it's important because now we have only one bare yield in the entire program, and that is buried deep inside async sleep. Right? That's an important quality. So we can have plenty of yield froms, but only one yield. So our other coroutines are now relying on async sleep. And of course, we know it's a refactoring, in spite of my total absence of tests here, because it behaves exactly the same when we run it. We schedule our repetitive message, Actually, it's not refactoring from the last demo video I showed you, because we've now fixed the isPrime function to be interruptible. So now you can see we're finding the prime Lucas numbers and we're printing the messages, and both of those tasks are nicely interleaved because all of our functions are coroutines and therefore they are non-blocking. Now, in the 90-minute version of this talk, I make you wait for the next prime number, but we only have 60 minutes today, so we'll keep going. Okay, so at this point, I have built something that is functionally equivalent to some very important pieces of Python 3's async I/O without using any async I/O. It's just generator functions and a super simple scheduler that literally fits on one slide. Well, what I'm going to do in the next part of the talk, part 3 of the talk, is take that code I've just written and transform it, actually mechanically transform it, into legitimate Python 3 async I/O code. And I think this is important because it demonstrates that there is no magic in async I/O, right? You've just seen all the magic, and it's like all of these things. Once you open the box and understand what's inside, it's really, really very simple. So on this slide, I'm showing you, I think, all of the code except for the scheduler, which I've created up to this point, all the functions there, and I'm going to mechanically refactor this. So the first step is every time I've written def async foo, we are now going to write async def foo. Okay? So we're using some keywords that came into Python 3.5 here. So you can see all my coroutines are now async def. The next thing I'm going to do is just import async I/O. The reason I imported async I/O is so that I can call async I/O's sleep function rather than my sleep function. So I'm going to replace all the calls to async underscore sleep with async I/O dot sleep. So that's that. Now I've done that, I'm not using my sleep function, so we can get rid of that and have less code, which is great. Finally, I'm going to replace all occurrences of yield from with await, which is another new keyword in Python 3.5. So now we have this, okay? And this is a completely mechanical refactoring. Obviously, I did this by hand. I mean, you could imagine writing a program to do this. It's very, very straightforward. So let's see what behavior we get now. The invocations here are a little bit different because now I'm using some async I/O stuff. So I get the async I/O event loop. I no longer need my own scheduler here. And I now call create task. You can see it returns a task object. That's an async I/O task object, not one of my task objects. But it's essentially exactly the same idea. So now with their scheduler, I can run forever. And you see we get exactly the same behavior that we just had, except now we're using Python's event loop and Python's tasks and Python's futures and all these other things, rather than the very simple ones that I showed you previously. Turns out that the Python ones aren't actually very much more complicated conceptually than what I've showed you earlier. So let's not wait for the big prime numbers. So having understood the concepts of how async I/O and async and await work in Python, it turns out that async and await in Python are implemented essentially using generator functions. We can move on a little further and see what else async I/O library gives us for working with these kind of objects. So async I/O, in async I/O, coroutines are used to implement tasks. Coroutines await other coroutines. We have an event loop which schedules concurrent tasks. Tasks must not block. Awaiting facilitates context switches between the task. Every time you await, that's an opportunity, that's when you yield control back to the event loop. And it may choose to continue running your task or some other task, but you can be sure that eventually control will come back to you. And in async I/O, you're not allowed to use the bare yield. If you just want to yield control to the scheduler, the way you do that is by awaiting async.io sleep 0, which, as I've shown, is equivalent to that bare yield. Just a note on terminology, I find people aren't very precise when they're writing about these things in documentation, which can be very confusing sometimes. So the thing on the left is a coroutine. It's a bunch of code, and it's callable, we call it. The thing on the right is a coroutine object, which is the code plus its execution state. It's executing code. And those things are awaitable, which is a new concept in Python 3.5. So if you are writing documentation about these things, please try to be precise, because then I can understand your documentation. So async.io gives us some other tools like futures. So a future encapsulates the idea of a potential result or a potential error. So here I have the coroutine there, monitored search, which, as you can see, just delegates with a weight to the search I wrote earlier, except that it also accepts a future object. And the future is essentially the future. We can either set it with a result to say, yes, the potential result has been realized, or we can call set exception and say an error occurred. So it's a signaling mechanism that we can use to communicate between tasks. I also have another coroutine there, monitor future, which will accept the same future object, and every interval seconds will print out the state of that future. So if the future is not done, so while future not done, print waiting, okay? And you'll see the main program down at the bottom there, I have that call to create future. When I pass the same future instance into monitored search and monitor future. So we're going to run these two tasks simultaneously, but they're both using the same future instance to essentially communicate. You'll also notice when I run this on the right there, we get an error from async.io, the event loop, saying, hang on, when this program finished, there was a task destroyed. I had to destroy a task, but it was still running. It hadn't completed cleanly. We'll come back and fix that error later. When you're creating futures in async.io, there's a very tempting constructor, which is the future constructor, and you should really avoid calling it. The problem with calling the constructor is that event loop implementations, and there are several, are allowed to specialize the future implementation. And if you call that constructor directly, you bypass that specialization. So you should always call a factory function instead on the event loop, which gives the event loop the opportunity to give you a different future. So for example, the way the event loop is implemented on Windows is completely different from how it's implemented on Unix. So the implementations of those features can then differ when we call this factory function. Turns out, in what I view as a particularly dubious use of inheritance, which is not the first time this has happened in Python land, is that a task is a future in async.io. So we don't necessarily have to create futures in order to monitor their progress. We can actually just directly monitor a task. So I've changed my program on the right here so that it no longer creates the future. We no longer need to do that. And where we monitor the future down at the bottom, I have loop create task monitor future. We actually pass the search task in directly to monitor it. And we're allowed to do that because the task is a future. The reason I say that this inheritance is dubious is that calling things like set exception on a task is something you should never really need to do. I think it's a pretty questionable API design. Yeah, so there we are. The task is a future, so we can directly monitor the task rather than the future. When it comes to creating tasks, again, there's a very tempting task constructor. And for the same reasons as futures, you shouldn't ever use this, even though it's there in the API, because for the same reasons. It prevents the event loop specializing the implementation. You should prefer to call the create task factory function. Even better, and in a particularly confusing way, the correct way to create a task in async.io is to call a thing called ensure future. Right? This is obscure, but it is the right way to do it. It's more general in that it accepts awaitables, not just coroutines, and it's also idempotent, so it will avoid wrapping the same task up in more and more tasks if you happen to call it more than once. So yeah, in spite of its confusing name, it does actually return a task. So if you get the sense that some of this was kind of released to the world prematurely, but now we can never go back and fix the API, I would agree with that. So there we are, using ensure future to create our tasks. So that's the right way to do it. I definitely need a new battery in my clicker. I need to stand here. So I pointed out earlier this bug, if you like, in my program that one of our tasks is not being correctly wound up. That's because our search task completes. And if you look at the bottom of my main program there, I'm doing run until complete search task. So as soon as the search task is complete, we exit, but the monitor task is still running. So we would like to wind up the monitor task gracefully rather than just killing it. So to do that, we want to wait. To do that, we want to wait for more than one task. And the way we do that in async.io is using this gather function. You can see at the bottom there. So gather allows us to combine multiple futures into one, essentially. It says, give me one future that represents the completion of all these other futures. So I've created a I've created a future called search and monitor future by gathering the search task and the monitor task. And now, when I do that, we get the graceful cleanup. Gather accepts any number of awaitable objects, which includes futures, tasks, coroutines. Okay, we haven't talked yet about I/O. So if you look at the event loop API, it's huge. It has all this stuff in it, starting and stopping the event loop, scheduling callbacks, factories I've told you shouldn't use, configuration stuff you rarely need. That's not even the half of it. There's exception handling, there's diagnostics, there's signal handling. We can run blocking code in other threads or processes. There's low-level socket operations in there. This is all one class. It's incredible. There's even more. There's protocol-based SSL, TCP socket servers. We can watch file descriptors. We can connect to pipes. This is a very substantial public API to the abstract event loop. But the question is, what's all this I/O stuff doing in the event loop? So finally, we get onto I/O. So we've got this far talking about coroutines without really talking about why we care. Well, the reason all this I/O stuff is in the event loop is to do with when tasks are run. So the scheduler I built earlier was this super simple round-robin scheduler. It just clocks around the tasks, running each in turn. The tasks just run in a very simple circular order. If instead we had an I/O-aware scheduler that could use epoll or select on Unix or I/O completion ports on Windows, we can be a bit smarter about when we schedule the tasks, and we can distinguish between tasks which are ready to run or are waiting on I/O. So essentially, that's why we have all this I/O-related stuff in the event loop API. It's because we have an I/O-aware event loop, which can be a bit smarter about when it runs things. So it will skip a task which is waiting on I/O, but then when the data becomes available, we can immediately go back and run that before proceeding. So it enables us to be smart about scheduling, which enables us to reduce the latency. Okay. So the async.io library in Python has this pretty substantial tower of abstractions layered upon top of each other. We've seen at the bottom that we can build resumable and suspendable functions, coroutines, using generators. On top of that, we have tasks, which in conjunction with the IO-aware event loop, can await on sockets and file descriptors and things. On top of that, async IO gives us transports and channels, which are a higher level abstraction. When I'm dealing with a transport, I don't need to care about whether I'm dealing with a file or a socket or a pipe. It's kind of one level of abstraction up from all of that. On top of that, it layers a thing called protocols, which deals with the life cycle of connections. So connected, a connection created, we're working with a connection closed. And on top of that, we have another coroutine-based API, which is a much higher level use of coroutines. So we have 10 minutes left. Let's see if we can quickly get through some of these. I'm going to show you the protocol-based API quickly without a demo, and then I'll show you a stream-based API with a demo. So this is a simple chat room, which is going to consist of two classes, this chat room class and a protocol class. And you can see that the chat room is very simple. It has a name, it has a port, which we listen on, an event loop, and some mapping of usernames to transports, these async IO transport objects. When we run the server with this create server call to the event loop, we give it essentially a callback, and it will call this, it will instantiate a protocol instance for each new connection to the chat room. And you'll see this protocol class in just a moment. And then there are some functions in here to deal with new connections, where we register users and deregistering users when they leave the chat room. So all this is on GitHub, so you can look at it later in detail. But it's a very simple thing. What's important here is the protocol, which I said protocols are a callback-based API. So here's the protocol. One of these is instantiated for each new connection to the chat room. You can see it has a reference back to the chat room, and it corresponds to a particular username, and it will own a transport, which is the actual channel that we can use to communicate with the user. Here are the three functions that will be called, and the little state machine here. So async IO will call, on your protocol, it will call connection made exactly once, it will call data received as many times as data arrives, and it will call connection lost exactly once when you finish. The problem with working with these protocol-based API and async IO is you have to do a lot of work, particularly dealing with text data, in doing things like finding ends of lines, because you're just getting a chunk of bytes that arrives at you over a socket, basically. And it's up to you to find the frames of data within that. So it's relatively low level. I'm not going to go through all this now. I guess what's important here, as you saw in that note that's just flown by, is that because only one of these coroutines is running at any given instant, we don't have to look any of the shared mutable state, right? Because we know that nobody else is modifying that at any given instant. So we have shared mutable state between tasks, but we don't need to look. Okay. So normally I would give a demo here. I'm a little short of time today. I'm not going to give you a callback-based demo, but I'll show you the stream-based demo. I don't need to do both demos because the user experience of the demos is identical. So that was the callback-based protocol stuff in async IO. Let's look at a coroutine-based one. And the coroutine stuff is much nicer to work with for this reason, is that we can avoid some really horrible nested callbacks and this pyramid of doom that you get with this kind of nesting here, where we're awaiting tasks on callbacks. Await allows us to transform that kind of horrible code on the left into something exactly equivalent in the form on the right. I hope you'll agree it's much easier to read and reason about what's going on and easier to get right. So what I just showed you are the protocols with those three callbacks, connection made, lost, and received, was the protocol level API. Let's look at the stream-based API. This is exactly the same program, chat room. We can do it in one class now. What's important here is that the run method here, start server, does invoke a callback client connected, and that's a coroutine. And that coroutine will be called once per user connected to the chat room. Let's just look at that client-connected routine. What's interesting is this function can take a very long time to run. If you connect to the chat room for a week, it takes a week to execute this function, right? This function, this coroutine, client-connected, is the entire life cycle of a particular user's connection to the chat room, okay? So you can see when they arrive, we say welcome. Then we just await user registration. We're going to ask them to register, and we just sit there and wait until they register. And because we're using await, other connections have opportunity to come and go. Then when they're registered, we tell everybody else that a user has arrived, and then we await user activity. So other people can be using the chat room. And then eventually, the connection will be closed, and they will leave. That might be a week later, right? Might be a month later, okay? And then we deregister the user, and then we're just some housekeeping at the end. We just drain our writer so that there's nothing pending in outgoing buffer when they leave, okay? So I think it's very interesting that you can have these coroutines which can take a very, very long time to execute. I think the idea of, we have these ludicrously fast computers these days, and the idea of having a function that takes a week to run, which does almost nothing, is kind of fascinating. So I will demonstrate, I think we have a demo. Yeah, the rest of this is just housekeeping. I will use my last 4 minutes to give you a demo. So you can see the entire chat room is a very simple thing. Okay. So here I have I've got the callback-based chat room and the streams-based chat room. I'm going to run the streams-based demo for you here. And here's just the class I just showed you. Here's the client-connected coroutine that might run for a week. I'm just going to run this here. The server's now running. We'll just switch over to a couple of terminals here, and it's just using Telnet, right? So nobody uses Telnet these days, so I like to keep it in use. We're running on port 1234. And when we do this, that coroutine has started running. And you remember, pretty much the first thing it did is says, welcome to the chat room. Here's the message, and ask me for my name. It's now awaiting user registration. So who am I? I am Sheila today. User Sheila has arrived. And then we'll Telnet again over here. And who am I now? I'm Jim. And you can see that the message has been sent to the other chat room, and we can say, hi, Sheila. So now both of these coroutines are running simultaneously, and they're alternately doing await user activity. So every time we type something into one of these, who was it, Jim, we do the work of that coroutine. Eventually, I close the connection. We do that in Telnet like this. When I quit Telnet here, you'll see that coroutine ended. So one of those coroutines is now finished running. The other one's still going, and you see it picked up the message for Jim departed. So there we are. That's the demo. Very straightforward. I think I'm going to stop there because we have like a minute left. I will remind you to come up and get a free copy of my books. And thank you very much. We have a minute or two for questions if you're quick. Thank you. I am aware of C# async await, and I have never used it in anger. I mean, I've done quite a lot of C# programming. What I'm not sure of with async await in C# is what the underlying mechanism is, whether it works this way or a different way.
And then my other question is, I guess mostly how I've used it in C# at least is I've never really written my own coroutine. I've used a lot of existing packages from people. Has the Python community sort of grown up and started building async?
Absolutely. So, I mean, I mentioned at the beginning that I am the maintainer of PySerial async.io. I've recently started using a thing called AIO HTTP, which is the most horrible name to say. But it's a really nice HTTP server using asyncio and very good performance and very easy to use. On Tuesday, I was using the asyncio package for the Kafka API. Okay, so the community is definitely stepping up and producing asyncio packages for basically anything that deals with asyncio. So it's taking time, but certainly over the last year, it's begun picking up momentum. Any more questions? No? Okay, thank you very much.